So I'll just start with a few logistic points. The first is that homework 4, which is the last one, will be released today. If it hasn't, it should be like within the next hour, I guess. And it will be due in 2 weeks from now, so it will be Wednesday in 2 weeks. And that's the last homework. It's going to have 3 theoretical problems and 1 programming problem. And the theoretical problems, I think, will be slightly harder than like the average theoretical problem in previous homeworks. The programming problem will be a bit easier than the average programming problem in previous homeworks. So I guess this last homework will be a bit more theoretically oriented, a bit more challenging in that sense. Yes, that's one thing. The other thing is in the last lecture, we're going to have Q&A. And the way it will work is that we're going to ask you guys to ask thoughtful questions about the course. And then we're going to look at the questions that you ask, and we'll choose a subset of them. And then Zico and I will sort of answer these questions in the lecture together. So just to give you a heads up to expect this, so I'm going to post a post on Piazza at some point, just soliciting these questions. And I'll give a few examples for what like thoughtful questions might be. But of course, you're not going to be graded for this. We may sort of check that you actually did submit a question as a kind of participation, but there's no grade for your question, so feel free to be, to sort of ask anything that you think is interesting or fun, and then we'll just choose like a subset of these questions.
This is for the class on May 3rd.
Oh, on May 3rd, yeah. So that's the last lecture on the schedule. Yeah. Okay, so today we're going to do the last social choice lecture, social choice 3. And as promised, this lecture will be, I think, a bit more with an eye towards applications and thinking about the case where we have objective opinions and then how do we want to design voting rules and aggregate that type of opinions. So our starting point is again going to be Condorcet. Remember that when we talked about Condorcet in the context of Condorcet consistency, Condorcet winners, and so on. So that's one important viewpoint that Condorcet sort of gave on voting. But there's another very important contribution that he made to how people have thought about voting for the last centuries, in the seminal work in 1785. So his viewpoint was that there's some truth in terms of, he was thinking about politics, but he was saying, some candidates are like actually better than others. There's some truth. And then when you have enlightened voters, their purpose is to try to judge which alternative is the best alternative. I think maybe try to close the windows because it's even noisier than last time. So, so he was saying, let's think of these voters who are trying to evaluate what's best for society. So this is a really very optimistic viewpoint of like what voters are thinking about when they're voting. But that's a viewpoint that he took. And one very important and well-known theorem that he proved is what's called the Condorcet jury theorem. That I'm not going to state it formally, but essentially what it says is it's the following model. You have, think of a jury who are trying to determine whether a defendant is guilty or innocent. So there are 2 answers. One of them is correct, one is incorrect. And let's say that every juror has probability p greater than 1/2 of voting correctly, of like determining the correct answer. And with probability 1 minus p, which is less than half, the juror votes for the wrong answer. And what Condorcet proved is that as the number of jurors goes to infinity, the majority opinion will be, the probability that the majority opinion will be correct goes to 1. So this is something that in today's, with our understanding of probability today seems pretty trivial. We can prove much stronger bounds in the rate of convergence and so on, but in 1785, probability theory was just getting started. So this was like a pretty non-trivial statement to prove at the time. But again, it's a very intuitive statement, and it really serves as some kind of justification for voting in these situations where you have a ground truth and people are trying to determine it. So at least if you're saying, the jurors are at least have probability better than just a random coin flip of like figuring out the right answer, then the system will work and the majority opinion will be correct. So that's what, that was the starting point of Condorcet. We'll talk about like how we try to extend it rather unsuccessfully. But what I want to mention is that this is, like we said, realistic in trials by jury. It's not so realistic in political elections. It's hard to say in a political election if some candidate is like the true best candidate and other candidates are less good. But other situations where this is very relevant are, for example, when you pool expert opinions about certain issues, which I'll give you examples of, and also in human computation. So I want to give you two concrete examples in which, voting in a situation where there is a ground truth makes a lot of sense. So one example that I really like is a citizen science game called Eterna, which was developed at CMU and Stanford. The idea in Eterna, some of you may have heard of Foldit, which is a related game. It was sort of came before Eterna. Eterna has some additional really nice features. So the idea in Eterna is you want to design RNA molecules by putting bases together, the 4 bases, in a way that would fold into a target shape. So basically the game is you're given some target shape, and you want to design the molecule such that when it folds in nature into a stable structure, that structure will be the target structure. So that's on a very high level what the game is. So it's sort of a puzzle game, but they've really developed it over the years to, to get people involved in developing new medicine and so on. It's a really, really inspiring concept, I think. So one really novel feature of this game is that every week they have thousands of designs for the target molecule that get submitted, and they can only synthesize 8 of them in a lab in Stanford Medical School. And the question is, which 8 designs should we synthesize? So the way they do that is using voting. They use a simple voting rule called 8 approval, which means that every voter has 8 points, which he gives to 8 different, to his 8 favorite alternatives. And then the 8 alternatives with the most points win the election and get synthesized in the lab. Now, the one thing to note about the setting is that here there actually is a ground truth, because there are measures of how stable the structure actually is in nature, and these are sort of agreed upon objective functions. So there is an objective metric to assessing how good each alternative is once it gets synthesized. And really what the voting rule needs to do is identify, based on the votes, the alternatives that are actually good in reality. So one question you could ask in this context is, okay, they're using 8 approval, but if we think about this in the way that I just stated, how do we design better voting rules that are more likely to choose the best alternatives, the one that have, the best quality in nature? So that's sort of one example, and these kinds of examples come a lot in human computation, in these situations where we sort of have programs that get input from humans to solve problems that computers find hard. So often these are situations where voting is used and there is a ground truth, and the question is, which voting rule you want to use. So another example is close to my heart, is this website that I mentioned when we talked about social choice initially, RoboVote. And if you recall, I mentioned there are 2 types of applications on RoboVote, aggregating subjective preferences and objective opinions. So let me just talk in a bit more detail about the objective opinions case. So here really the target is helping groups of people make decisions, but objective opinions are cases where these people have where there is a ground truth and these people have objective opinions, trying to estimate some objective metric. So to give you 3 examples that I like. One is a group of engineers and managers working in a company, trying to decide which product prototype to develop. So the idea is if it's several cell phone prototypes, you're not ranking them based on how much you would want to use each possible product, but based on some metric like what would be the market share of this prototype if we chose this one for development. Right, so this is a situation where you won't actually find out, you're not going to develop the other prototype, so you won't actually find out how well each prototype did. But there is a ground truth in the sense that if I chose prototype A, it would have a market share of 40%. If I chose prototype B, it would have a market share of 42%, and so on. And the job of the experts is to predict which one would actually be best in practice. Another example, investors working in an investment firm trying to decide which company to invest in based on some objective metric like projected market share or projected revenue. So again, each of these companies, if we ask about revenue in the next quarter, there is some number, we don't know what it is, and we're trying to pool our opinions, aggregate them, and figure out what's the best option. Or, movie executives in a movie studio trying to decide which movie script to produce based on box office earnings. Okay, so you can come up with many examples like this. All of them are, when there's some objective metric, but it's unknown, the quality is unknown, this is the type of situation that the methods that we'll talk about will deal with. So what we're going to do today is I'll just give you the basics of how to reason about these situations. We won't go all the way to like the methods that are actually deployed, but at least I'll give you the basic tools that you need in order to reason about how to do this. And our starting point is going to be the work of Condorcet, which will also give some opportunities to talk about the interesting history of this viewpoint. So the setting that we're thinking about, and this is Condorcet's setting, is we have a true ranking of the alternatives. And our goal is actually going to be to output a ranking. So instead of outputting a single alternative like we did in the last two lectures, we're going to look at rules that output a ranking of the alternatives. And on a high level, we want to output a ranking. The ideal would be to output a ranking that coincides with the true ranking. So we want to identify what the true ranking of the alternatives by quality is. Now, the voters, the input here for now is going to be slightly different from what we did before, and then we'll convert this to the regular type of ranking input. But for now, the voters are going to vote pairwise on alternatives. So they just compare pairs of alternatives. And the comparisons don't have to be transitive. So a voter may end up saying, I think A is better than B is better than C, and C is better than A. So it may not correspond to a ranking. But the model is, we have some probability P greater than 1/2. And every time a voter compares a pair of alternatives, he gets them in the right order with probability P, and in the wrong order with probability 1 minus P. And then we're telling the results in a voting matrix like the one on the right. So what is this saying? This is just saying, the number of voters here is 13. And each entry is saying how many voters prefer the alternative in the row to the alternative in the column. So for example, if you look at A versus B, 8 voters prefer A to B, and 5 voters prefer B to A. And together, it's like the total number of voters. Like everybody either prefers A to B or B to A. If you look at, A versus C, so 6 prefer A to C, and 7 prefer C to A. Okay, so again, it adds up to 13. Okay, so just, I want to give you a poll just to get you thinking about these voting matrices and the relation to rankings. So it's kind of a trick question. The question is if I told you that this matrix corresponded to rankings, that the voters actually had rankings, and then I looked at all of the pairwise comparisons in these rankings and tallied them up in this voting matrix, what would be the Bordas score of alternative B? Okay, so I'm going to open the poll. And remember, Bordas is the one where with 3 alternatives, it would give 2 points to the first place, 1 point to the second place, 0 points to the last place, and then we just add up the points. Now you already know my secret with the 60 votes. Don't use it against me. Sorry? Yeah, so the table shows every entry is how many voters prefer the alternative in the row to the alternative in the column. So for example, the 8 here says, if you think of this as like summarizing rankings, it would say 8 voters ranked A above B, whereas this thing would say 5 voters ranked B above A. So far, I mean, this poll is independent of this probability. Okay, so it's just, I'm just telling you, like, people have voted according to some probabilities. They got this, the comparisons were summarized in this table. Okay, but then, the question of like, what's the Bordas score based on the table for now is independent of the probabilities. It's just, what you should have in mind is, if I had rankings corresponding to this table, what could I say about the score? Huh, 10 more seconds. Okay, interesting. So yeah, it's a pretty random split. So let me give you, I'll give you like another minute to think about it, talk with other people if you want, and you can revise your vote. Direction, still not a majority, but the right answer is 16. So what's a simple formula, like general formula for determining the Bordas score of an alternative in the settings? Sum the row, right? Okay, so why? So the answer is sum the numbers in the row for that alternative. Can anybody give an explanation for this?
Let's say if you have only 3 alternatives like this, just because it's simpler to explain. So for some candidates, B is in the bottom, so just get 0 points, and B does not include it in this counting at all. And then if A is if B in the second position and below is A, we count it once in the B row and A column. If C is below, then we count it in B row and C column. And then B is the first one, and there is A and C below, we count it in both
Excellent.
BA and BC.
Excellent.
And that's why I just
and the B gets 2 Bordas points, right? So, right, excellent. So what Alex is saying is, there's just if you think of any ranking, right, so you're saying, let's say B, even with more alternatives, let's say you have like B, and then x1, x2, x3, let's say, and some alternatives above. So here the Bordas score of B would be 3, right? And then what would happen here? So this voter, this is one vote, but this one vote would add 1 to the comparison between B and x3, would add 1 to the comparison between B and x2, and would add 1 to the comparison between B and x1. So overall, it adds 3 to the row of B, and the Bordas score given by this voter to B is 3. Okay, so this is sort of a general argument. Yeah, Brian.
Did you say there could be cycles?
Yeah, so
How do you deal with that?
so for now, we're actually not going to worry about it. So for the poll, I said, imagine this does correspond to rankings. But for now, we won't worry about cycles. And then, like in half an hour or so, we'll come back to the case where we do want the voters to give rankings. Okay, cool. So let's see what Condorcet suggested for this model. Okay, so what Condorcet wanted is to find the most probable ranking. You know, given these votes, you want to find the ranking that is most likely to be the ground truth. Now, what he suggested is to take the majority opinion for each comparison. And if a cycle forms, you know, the quote translation from French is successively delete the comparisons that have the least plurality. So let's see how this works in this example. So here, there's a majority. There are 13 voters overall. A majority prefer A to B. A majority of 11 prefer B to C, and a majority of 7 prefer C to A. So here, there's a cycle in the preferences of the majority. And what he said, okay, so now delete the comparisons that have the least plurality. So of these 3 comparisons, C versus A has, you know, just more than 1/2. That's the weakest comparison of the 3. So Condorcet suggested, okay, let's delete this arrow. And then we get A is better than B, B is better than C. So this gives us a ranking. And then, you know, the proposal is let's return this ranking as our output. Okay, so that makes sense. It's not clear yet, like in what rigorous sense it makes sense, but it sort of at least it's consistent with, you know, it's like a consistent algorithm. But now let's think about the case of 4 alternatives. So now, you know, we have 25 voters in this example, and again, you know, we have this tally of the votes of the pairwise comparisons. And now, if we sort all of the pairwise comparisons by strength, you would get, you know, C versus D is the strongest comparison with 18. You know, that's the highest number in this table. And then the second highest number is 17, so A versus D, and so on. So this is sorting all of the pairwise comparisons by their strength. The weakest one is B versus A, which has 13, which is just you know, one more than you know, it's, you know, just over the majority. So what do we do? So we got this graph that tells us which, you know, for every 2 candidates who beats whom. And then Condorcet tells us we should start deleting comparisons based on the strength of support. So the weakest one is B versus A. So we start by deleting this edge. But we still have a cycle. Let's actually make sure, you know, in this graph there is a cycle. There are a couple of cycles. So we delete this edge. But now we still have a cycle, B, C, D, for example. So Condorcet tells us we should keep deleting until we remove all cycles from the graph. So the next edge to delete is between D and B. So we delete this edge. At this point, we don't have a cycle. But it's also not clear to which ranking this graph corresponds. Because, you know, what we have is that A and B both beat C, A also beats D, but it's not clear what the relation between A and D is. So, you know, in a ranking that is sort of consistent with these comparisons, we can put A first or put B first. It's not clear what we should do. Okay, so, you know, here's another interpretation of what Condorcet said. So, you know, maybe it meant that we need to reverse the weakest comparisons instead of deleting them. So let's try that. What we have to do in order to get rid of the cycles is we start by reversing the edge between B and A. We still have a cycle. Then we reverse the edge between B and D, and we end up with this graph. So this graph is actually good in the sense that it does induce a ranking. So it's clear that here, right, we get A beats everybody, then B beats C and D, C beats D, and D loses to everybody. So the induced ranking is A, B, C, D. So at least it's like not ambiguous which ranking this graph, this tournament corresponds to. But now is this the right ranking? Like we were sort of being pretty greedy in how we reversed edges. So for example, one way to measure like the quality of the ranking is to say, let's look at how many voters agree with these pairwise comparisons. So like this ranking says A is better than B, A is better than C, A is better than D, B is better than C, B is better than D, and C is better than D. And if you look at the table and add up all of these numbers, A versus B, you have 12, A versus C, you have 15, and so on. If you add all of these numbers, you get a total of 89 votes that support these pairwise comparisons. On the other hand, if we only reversed, instead of being greedy and like first reversing the weakest edge and then D versus B, we could have just reversed D versus B and eliminated the cycles in the original graph. Right? Like if you look at this graph, it's enough to just reverse this edge and then you eliminate the cycles in this graph. So we could do that. And that would actually be better in terms of this objective of like trying to agree as much as possible with the voters. It would have 90 votes instead of 89 if you sort of look at how many people support all of these pairwise comparisons. So, so it's okay. I mean, it's sort of a valid interpretation. It gives rise to a ranking, but in what way is it optimal? Like we're trying to look for the most probable ranking. It's not clear that this algorithm proposed by Condorcet, or this interpretation, is actually optimal in any reasonable way. So this problem, this ambiguity with what Condorcet proposed, actually confounded, scholars, mathematicians, and people, historians of science for centuries. And there are pretty amusing things that people have written about it over the years. So for example, Black, who was well-known political scientist, wrote that the general rules for the case of any number of candidates as given by Condorcet are stated so briefly as to be hardly intelligible, and as no examples are given, it is quite hopeless to find out what Condorcet meant. And then Todhunter was like a noted mathematician, went even further and said the obscurity and self-contradiction are without any parallel so far as our experience of mathematical works extends. And then he followed up with this sentence that is my favorite: no amount of examples can convey an adequate impression of the evils. So this guy was really, really, you could feel his frustration with Condorcet, probably spent years like trying to figure what the hell Condorcet meant. So this was like really frustrating to many people for centuries. So finally in 1988, Peyton Young, who's a well-known scientist in many areas, in social choice and political science, and has contributions in math, was really like a Renaissance man. So he figured out, or at least like came up with this solution, or the way to think about this, that is really like people think of this as the solution to what this puzzle of what Condorcet actually meant. Okay, so he managed to like really find a mathematical framework in which all of this makes sense. So here is the Young solution, and it's a bit confusing. It is closely related to other stuff that we talked about in this course and Bayesian reasoning, but it's still, I think, a bit confusing, so let's do this carefully. So like before, we're going to have this matrix of votes of pairwise comparisons that we call M. And let's suppose for a minute that the true ranking is A is better than B is better than C. Okay, there's some true ranking. Let's for a minute suppose that this is the true ranking. And I want to compute the probability of observing this particular matrix M, conditioned on the fact that this is the true ranking. So what is that? So let's see. So we have, if we look at A versus B, we have 8 voters out of the 13 who think A is better than B. Okay? So I'm going to choose out of the 13 voters, I have to choose 8. And then what's the probability that these particular 8 said A above B and the other 5 said B above A? Well, remember that the probability of agreeing with the true ranking is P, and according to the true ranking, A is actually better than B. So we have 8 of these guys are right? So we have P to the power of 8 and 1 minus P to the power of 5. Because we have 8 people who are right and 5 voters who are wrong. What about A versus C? So A versus C, the true ranking tells us A is better than C. And the matrix tells us we have 6 voters who are voting correctly. They say A is better than C. And 7 voters who are voting incorrectly. They say C is better than A. So, so we have to choose 6 of the 13 voters to be right, to say A above C. And then these guys, so these 6 voters are right with probability P to the 6. And the other 7 are wrong, say C above A, with probability 1 minus P to the 7. Okay? And finally, if we take B versus C, so we have 11 voters who rank B above C and 2 voters who rank C above B. So we have to choose 11 out of the 13 who will rank B above C. And then these 11 have probability P to the 11 of ranking B above C, which agrees with the ground truth. And the other 2 rank C above B, which happens with probability 1 over P, 1 minus P squared. Okay? So this is really a crucial point. Is it clear why this expression is the probability of observing this matrix if this is the ground truth? Yeah, Matthew.
What is P again?
So P is the probability that when a voter compares 2 alternatives, he will get them in an order that agrees with the ground truth. So at some probability, it's greater than 1/2. So it's your probability of any voter agreeing with the ground truth when comparing a pair of alternatives.
But that's not the same per voter, is it?
So the model is it's the same per voter and every pair of alternatives. Okay, so Condorcet's model is like we have the same P for all of the voters.
Okay.
Okay? And so every possible comparison, everybody gets it right. That's the model. Everybody, I mean, we can. I'll get back to later to the question of is this realistic? It's not. But Condorcet's model was like every pairwise comparison, people get it right with probability P, wrong with probability 1 minus P. Any other questions about why this expression is this probability? Okay, so let's do this again for a slightly different ranking. So now let's ask, what's the probability of observing this ranking if this ranking was the ground truth? Okay, so this is a similar ranking. It still ranks A above B, and it still ranks A above C, but it flips the order of B and C. Before B was above C, so now C is above B. So what's the difference? When we compare A to B, so it's still the exact same situation as before because we're asking like what's the probability that these 8 voters rank A above B? Well, they still agree with the ground truth, and the other 5 voters still disagree with the ground truth because this true ranking still puts A above B like before. So that doesn't make a difference. And A versus C, again, it doesn't make a difference because both of these rankings say that A is above C. So where there is a difference is in this third factor for B versus C. Right, so now we're saying, we have, so the ground truth is saying that C is above B. We have 2 voters who think that C is above B. So we choose 2 out of the 13 voters to agree with the ground truth, to put C above B. That happens with probability P squared. And then the other 11 voters have to disagree with the ground truth, which happens with probability 1 minus P to the 11. Okay, so the only difference between the 2 rankings is C versus B. So the only difference between these 2 expressions is this last factor. Okay, so let's stare a bit at these 2 expressions. Okay, so one crucial point is that the binomial coefficients are exactly the same. So of course, these 2 are really exactly the same. They say exactly the same thing. But these 2 are also the same because 13 choose 11 is exactly the same as 13 choose 2. Right? N choose k is the same as n choose n minus k. So the binomial coefficients are exactly the same. The only difference is the powers to which we raise p and 1 minus p. So what are these powers? Right, so notice, what is this thing? If we ignore the binomial coefficients, we have p to the power of 8 plus 6 plus 11 times 1 minus p to the power of 5 plus 7 plus 2. And this thing is, again, the binomial coefficients, which are the same, times p to the power of 8 plus 6 plus 2 times 1 minus p to the power of 5 plus 7 plus 11. Okay? So the only difference here is that, notice that these numbers sum up to the same thing. The only difference is what's the power of p and what's the power of 1 minus p. And when I moved from here to here, so the power of p decreased by 9, and the power of 1 minus p increased by 9. But because p is greater than 1/2, that led to a smaller probability. Right? So this probability is going to be higher than this one because p is greater than 1/2. We have faith in our voters, and we do think like they do these pairwise comparisons with probability. I mean, they get them correctly with probability more than 1/2. But to summarize, what we get is that this probability we're interested in of what's the probability of observing these votes, these pairwise comparisons, given a certain ranking as the ground truth. So that's going to be proportional, because the binomial coefficients are the same, to p to the number of, what is this thing? It's a number of agreements of the pairwise comparisons with the ground truth. Okay, so the number of agreements of these pairwise comparisons with the ground truth times 1 minus p times the number of disagreements of these pairwise comparisons with the ground truth. Right, so for example, here, so all of the guys, so we had like how many people here agree with the ground truth. It's all of the guys who rank A above B, these 8. All of the guys who rank A above C, these 6. And all of the guys who rank B above C, these 5. So the number of agreements is 8 plus 6 plus 5, which is 8 plus 6. Plus, what was I looking at? B versus C is 11. So 8 plus 6 plus 11. Okay. So it's just like the number of agreements in the exponent of p and the number of disagreements in the exponent of 1 minus p. Okay. So I think this is probably the most important slide of the lecture. Is everybody okay with this? Okay, cool. So we have this. So now what we're actually interested in is, remember, we want to choose the ranking that is most likely to be the ground truth given the observed votes. That's what we're really interested in. But this is something that we've seen several times before. This is just Bayes' rule. So, this probability, which is what, we want to choose the ranking that maximizes this probability of being, the ground truth given the observed votes. But what is this? This is nothing about the probability of observing these votes given that this is the true ranking, times the probability that this is the true ranking divided by the probability of observing these votes. So we want to maximize this. Now, one thing to note is what we're doing is we're looking at what is this probability when we change our choice of ground truth. Now, notice that the denominator is the probability of observing these rankings. That's going to be the same, like no matter what we choose here. So we can ignore that. We can just say like this probability is proportional to the stuff that we have in the numerator. Now, another assumption that we need to make is we're assuming a uniform prior over the different ground truths. So if you don't have any information, every ranking is equally likely to be the true ranking. We're basically saying, for every ranking, the probability of this being the ground truth is 1 over m factorial, so they're all equally likely. So that means this thing is always constant. It's just 1 over m factorial, which means that the probability we're interested in, like we want to choose the ranking that would maximize the probability of observing the votes given that ranking. And that's exactly the probability that we computed in the previous slide. Okay? So let's, let me just recap. Right? So what we said was we want to choose the ranking that maximizes the probability given the observed votes, given our data. And what we're saying here is, to do that, we need to choose the ranking that would make the votes most likely, given that it is the true ranking. And that probability is proportional to this expression. Okay, so in other words, what this is saying is, in order to choose the most likely ranking, will be the one that maximizes the number of agreements with the observed votes on pairs of alternatives. Okay, that's a conclusion from these two slides. So again, the optimal rule is the one that maximizes the number of agreements with voters on pairs of alternatives. Let me actually. Okay. So let's say this way. We'll talk about an equivalent formulation in a minute. But one way to think about it is it maximizes the number of agreements. And notice that the number of agreements and the number of disagreements add up to the same thing, right? For every voter, like the number of people rank A, for every pair of alternatives, the number of people who put X above Y and Y above X add up to the total number of voters. When we look at all of the pairs, it's going to be the number of pairs times the number of voters. So, so maximizing the number of agreements or minimizing the number of disagreements, that's going to be the same thing. Right, and what we're saying is, in order to choose the ranking that is most likely to be the ground truth, given the votes, what we need to do is maximize the number of agreements on pairs of alternatives. This rule is called the Kemeny rule. Okay, so this is a rule that takes as input a matrix of pairwise comparisons. It could also take as input rankings. And it outputs a ranking which maximizes the number of agreements with these pairwise comparisons.
Why is it called the Kemeny rule?
After Kemeny, who's the guy who came up with it. That's the name of a person.
I guess my question was, you said Kemeny came up with this, but we're dealing with Young.
Right. So actually, some people refer to this as the Kemeny-Young rule. So Kemeny sort of came up with it independently a few decades before Young. But not from this viewpoint. Just saying, this has some nice social choice properties. It's sort of an interesting rule. And then Young sort of rediscovered it. I mean, I think he knew about Kemeny's work, but he said like, oh, notice that this rule is actually like the maximum likelihood estimator under this Condorcet model. So actually, a lot of people refer to Kemeny's rule as the Kemeny-Young rule. But Young was not the one who first came up with this rule. Good. Okay, so I want to define the Kemeny rule in a slightly different way, and this is actually something like that's going to play a role in your homework. So I'll point your attention to a few slides that will play a role, I think, in the toughest theoretical problem in the homework. So you should really pay attention, like in these slides. Okay, so what I want to do is define the notion of distance between rankings. Okay, so let's say I have two rankings, greater than and greater than prime, squiggly greater than. So I want to define a distance function on the set of rankings. And the distance between these two rankings is defined to be the number of pairs of alternatives such that one ranking, so pairs A, B, such that the first ranking puts A above B and the second ranking puts B above A. So, so it's basically the number of disagreements between the two rankings on pairs of alternatives. Okay, so it's a very intuitive concept of distance. It's like the number of pairs of alternatives on which the two rankings disagree. So another way to think about the Kemeny rule when applied to rankings is the Kemeny rule chooses the ranking that minimizes the sum of Kendall-Tau distances to the rankings in the given preference profile. So if you're given like a bunch of rankings as input, the Kemeny rule looks for each ranking. You want to minimize the total number of disagreements with all voters over all pairs. So that would be the same as saying for each ranking, let's look at the sum of Kendall-Tau distances to each vote in the given input profile. And we're going to sum over all of these Kendall-Tau distances. Okay, so an equivalent formulation of Kemeny is choose the ranking that minimizes the sum of Kendall-Tau distances between the ranking that you choose and the input votes, these rankings in the preference profile. Okay, so just, all this is saying is Kemeny can also minimize disagreements instead of maximizing agreements, and more formally, minimizing disagreements with all voters over all pairs is the same as minimizing the sum of Kendall-Tau distances to the input votes. Okay, so it's just like a slightly more formal way of saying the same thing. Okay, so that's the Kemeny rule. One thing that's interesting about it, it's actually a rule that has been considered in many different contexts. It's sort of known to be a good rule in many different ways. But one thing that's really tricky about it is that it's NP hard to compute. So this is from a paper by Bartoldi, Tove, and Trick, or the same trio who proved the result about Copeland with second-order tie-breaking being NP hard to manipulate. So they had like a nice few years where they discovered like this idea of complexity in social choice, and also noticed this phenomenon of like the Skemeny rule, which is really great, is actually NP hard to compute. So this is not about manipulation, just determining what's the ranking that minimizes the number of disagreements. That's an NP hard problem. However, it is not that difficult to solve in practice, and the way it's usually done is using an integer program. So I want to show you an integer program for computing the Kemeny ranking. So what we'll do is, for every pair of alternatives A and B, we'll have a variable xab, which is 1 if in our output ranking we choose to put A above B. So remember, like our goal is to construct a ranking, which is going to be our output. And then we have xab equals 1 if we're choosing to put A above B in our output ranking, and xab equals 0 if we choose to put B above A in our output ranking. But then, of course, xba will be 1. So for every pair, we actually have both variables, xab and xba. And then if we put A above B, xab will be 1 and xba will be 0. So that's, so of course, like an assignment, what we want to do is sort of write down constraints so that an assignment to these variables would correspond to a ranking over the alternatives. Now, another thing that we have is we have these constants, WAB, which are just defined by the given input profile, so they're constants. And they're just, WAB is the number of voters that rank A above B. Or in other words, if we choose to rank A above B, we're agreeing with WAB voters, and we're disagreeing with the rest, with N minus WAB voters. Okay, so these are constants. Basically, we're given a preference profile. We use it to compute these constants WAB. And our goal is to compute an assignment to these variables that would say what our output ranking is. What's the ranking that minimizes the number of disagreements? Okay, so how do we write this? So we say, we want to minimize the number of disagreements. So we want to minimize the sum over all pairs AB of xab times WBA. Right? And the idea is, if we chose to put A above B, then we disagree with all of the voters who think B should be above A. Right? So this is just, this is saying minimize the number of disagreements. And then the constraints are meant to ensure that these x variables correspond to a ranking. So they're very simple. This constraint just says, for every pair of alternatives, you need to put either A above B or B above A. And all of these variables are in 0, 1. Right? So this says, like, for every pair, it's either A above B or B above A. And this constraint is transitivity. So it says, in order to correspond to a ranking, you can't have a situation where A is above B, B is above C, and C is above A. So xab plus xbc plus xca is at most 2. It can be the case that all 3 comparisons are 1, because otherwise you would get a cycle. Cool. Okay, yeah, that's it. So that's the integer program for computing Kemeny, and I know that this has been implemented in different contexts, and it works quite well in practice, like if you want to use the Kemeny rule. Yeah.
So in practice, how many voters we have?
Yeah, so it depends on the application. So for example, some applications that people have implemented this for is, one is aggregating results from different search engines. One really nice thing about Kemeny is that it has this generalized Condorcet property that I mentioned in the first lecture. So then there the number of voters is pretty small. It's just like a few search engines. Another sort of just as an anecdote, I know that this is being used for PhD admissions in some schools. For example, I know it was used in Duke many times for CS PhD admissions. So there it's like the hiring committee are the voters. So it's maybe 10 people and a couple of hundred candidates. And it works it's very fast.
Yeah, sure. Yeah, okay.
Yeah, but if you want to spend an effort solving integer programs, you can definitely solve them with like hundreds of thousands of variables and constraints and so on. So these are like really relatively small numbers. Okay. By the way, there's quite a bit of work on other heuristics for computing Kemeny as well. So people have looked at this quite deeply, but this is sort of something that's pretty simple and works well in practice. Okay, good. So now we're going back to Pryor's question, which is, so far we were in some of the stuff we talked about so far, we're basically saying, in this model of Condorcet, we were saying, people just compare alternatives independently, and they may end up with something that is not a ranking. So now we want to refine this model into a model that actually says, voters will cast rankings, and then we again want to find the ranking that is most likely to be the ground truth. So this model is called the Mallows model. It's a well-studied model in statistics, named after a guy called Mallows. So a mistake many people do is call it the Mallows model, like the model belonged to Mallow, but the guy's name is actually Mallows. And the way it's defined is it has a parameter phi, which is strictly greater than 0 and can be at most 1. It can be equal to 1. And this is confusing. Let's stare at this a bit. So we're asking, if the ground truth is this ranking, what's the probability of a voter casting this ranking? Okay, so before we were saying, if the ground truth, how do we generate a vote? If there's some ground truth, we compare every pair of alternatives. So this gives us a formula for what's the probability that a voter casts a whole ranking given the ground truth. So what is this thing? So it's the parameter phi to the power of the Kendall-Tau distance between your ranking greater than prime and the ground truth. And this is normalized by the sum of this thing over all possible rankings. Okay, so intuitively what this is saying is the further away a ranking is from the ground truth, the more disagreements it has, the smaller its probability is. And the disagreements are again measured by disagreements on pairs of alternatives, so according to the Kendall-Tau distance. Right, so this is saying, a voter is less likely to cast some vote as the ground truth, the more disagreements it has as its vote, the more disagreements it has with the ground truth. So the only complication here is that because, it's sort of the same thing as before, but because we're forcing, we want this to be a probability distribution just over rankings, we have to normalize these probabilities in just like the most naive way. So we just divide this by the sum of all of these probabilities to get a valid probability distribution. So this is just a normalization term. Okay, so we're going to stare at this a bit more, but let me mention that you can sort of prove to yourself that Kemeny still gives the most likely ranking as the output when applied to, when this is the noise model. So the kind of reasoning we did before still works. But I want to think about this model a bit more in the relation to the model that we had before. So this is again the formula for what's the probability of a voter casting a vote given this ground truth. And remember that before we had this model where voters independently compare alternatives and get them right with probability p and wrong with probability 1 minus p. And the question is, what's the relation between phi in the Mallows model and p in the Condorcet model? Okay. So let's think about this a bit. For example, let's even draw a small table. So let's say if we have p equal to 1/2, right? Which means basically people are comparing pairs of alternatives uniformly at random. So like voters have no idea what's going on. Everything is like uniformly at random. What's the value of phi that would give you this kind of thing? Well, I'm hearing 1. Yeah, okay, so 1 is the right answer, right? Because if we have phi equals 1, it doesn't matter what the exponent is, like this will always be 1. So you basically get the exact same probability regardless of what your ranking is. So that means like every rank, given the ground truth, every ranking is equally likely. It's just going to be 1 to the power of whatever, the distance, it's going to be 1, and then you normalize. So it's going to be like a uniform distribution over rankings. On the other hand, if you take, let's say, p equals, we can't actually get p exactly 1, but p is sort of like almost 1. Right, so what would that correspond to? Like what value of phi? Very small, right? So very small phi. Why very small? So think of phi being really tiny, some really small epsilon. So if you think about the ground truth, if you put if greater than prime equals greater than, if it's the ground truth, then the Kendall-Tau distance will be 0, and then this will be epsilon to the power of 0, which is 1. But if this ranking even has Kendall-Tau distance 1 from the ground truth, this exponent will be 1, and then we get epsilon to the power of this exponent, which is much smaller than 1. Okay, so as that epsilon goes to 0, you can make this probability be completely centered on the actual ground truth, because this thing is much larger, right, for the ground truth compared to other rankings that are at Kendall-Tau distance at least 1 from the ground truth. So by taking phi as it goes to 0, that corresponds to p going to 1. Right, so this would be close to 0. In fact, if you take phi equals to 1 minus p over p, then you actually get an equivalence between the two models. So the way to think about it is if you think about the Mallows model with the parameter phi, this is equivalent to the Condorcet model, where every pairwise comparison is independent, and you can derive p from this in a way that depends on pi, so with probability p. But if we got unlucky and we ended up with something that is not a ranking, we restart. Okay, so this is basically the same model when you do this transformation. And the idea is that the normalization that we did in the denominator is sort of intuitively the same as this restarting phase. So we do independent coin flips for pairs of alternatives, but then if we didn't get a ranking, we do it again. Okay, that would be the same as normalizing the probabilities over all possible rankings. Okay. Cool. So just one interesting thing about the Mallows model, and this will actually be in your homework. So again, this is an important slide. Pay very close attention. So an interesting question is, how can we sample a vote from this model? Right? Because we're saying, these probabilities, so this is a probability distribution, if we know the ground truth, and now we just want to sample votes for the voters. We know the ground truth, we know the parameter phi, but we have this very large probability distribution over all possible rankings. So even representing it explicitly would be pretty cumbersome. Right? We need a number. We can compute the probability for every ranking, but then it's this very large probability distribution. So what I want to argue is that I want to give you a generative model for generating rankings, sort of iteratively, that would give you the same distribution over rankings as the Mallows model. And the model is called the random insertion model. The repeated insertion model. So how does it work? Let's suppose that the true ranking is A is ranked above B and B is ranked above C. So what we do is we start, this is the true ranking, and we're going to insert the alternatives of the true ranking one by one according to their positions in the true ranking. So we start with alternative A, and we insert it in the first position of the ranking that we create with probability P11, which equals 1. Right, so right now, we're just taking the first alternative, putting it in the first position. We don't have a lot of choice right now, but still to be consistent, let's say, this is happening. We're putting it in the first position with probability P11, which equals 1. Now it gets interesting in the second stage. So now we look at the second alternative that's ranked in the ground truth. And now we're saying, okay, we can either insert it in the first position with probability P21, or in the second position with probability P22. So with probability P21, we get the ranking B above A, and with probability P22, we get the ranking A above B. Okay, so let's say we chose to, the P21 thing happened, and B got inserted above A. And now we have C. So with probability P31, we put it in position 1. With probability P32, we put it in position 2. And with probability P33, we put it in position 3. Okay. So that's how the model works. And so this generates a ranking. And the challenge is to set these probabilities Pij in a way that would give you the same distribution of rankings as the Mallows model with parameter phi. Okay? And it turns out that if you set the probabilities Pij to be this thing, then this repeated insertion model induces the same probability distribution of rankings as the Mallows model with parameter phi. Okay, so this will be one of your problem 2 on your homework. So if you have any questions about what this model is, please ask now, or on Piazza later. Okay, is it clear how the model is defined? So we're just saying, we have these probabilities Pij, and every time we're saying, for the first alternative in the ground truth, we're putting it in position 1, and then for the second alternative in the ground truth, we put it in position 1, probability p21, position 2, probability p22, and so on. Okay, so really I didn't put it explicitly on the slide, but the point to remember is, we insert in the order of the ground truth. So basically, we want to generate a ranking given the ground truth and given the parameter phi, which induces the insertion probabilities. Okay, yeah, so this is a kind of tricky thing. We ended up breaking it into 2 parts. I think it shouldn't be hard, but it's harder than the average theoretical question that we have. Okay, cool. So that's almost all about the Mallows models. I just want to discuss for a few minutes, again, a question that came up before, I think related to Matthew's question, is this model realistic? So, the Mallows model, like Condorcet's model, basically says for every voter and every pair of alternatives, the probability of the voter being right or wrong on that pair of alternatives is the same, which is really crazy. In practice, you could have, we'll talk about some particular examples, but if you have, for example, in human computation tasks in online labor markets, some people are spammers, some people, there are some people who really are super diligent about solving tasks even if they get paid only 10 cents for it. And can spend a lot of time doing one ranking or one pairwise comparison. So the P's are going to be very different for different alternatives and different people. The model is far from reality. Nevertheless, it does say something about reality. So this paper from 2013 contains some experiments done on Amazon Mechanical Turk, which is an online labor market. It's this weird thing that has been used a lot for experiments, human subject experiments. It's a very cheap way of getting data. And usually, people really get paid, a few cents for performing some task. So it's, really very cheap. The kind of tasks in this paper were there were 2 types of tasks. The one that I like better is the one, this task. So it's basically, you're given an 8 puzzle, which is this, we talked about it in the context of search, right? And you're given the goal state, and you're given 4 states of the puzzle, and the task is to rank these 4 states based on how far they are from the goal state. How many moves would you have to make to reach the goal state? So that's a task. So the interface is you're shown the 4 states, then you drag them to this gray area in the order that you want to rank them. So this is a situation, of course, where there is a ground truth. Right? Each state has some distance from the goal state. And so it's really, of course, a setting with voting, with a ground truth. And it's, if you ask people, how did they solve this task? So some people said, I cut pieces of papers for different alternatives, and I sort of moved them around, actually solve the puzzle for each one of the states. Some people said I coded up a program that actually solves it. So people can spend a lot of time doing this, even if the payment is 10 cents. And obviously, some people just did it at random, just gave a random ranking. It's different people do it in very different ways. So this one uniform model is really wrong in that sense. And you can see that things don't match the Mallows model. However, the Kameny rule is really good. If the objective is what's the distance, what's the number of mistakes that the output ranking makes compared to the true ranking, right? So this is basically the Kendall-Tau distance between the output ranking and the true ranking, then the Kameny rule, which is the red line in several experiments and different data sets, does better than other rules. So this sort of says, okay, the model is not really realistic, but the Kameny rule actually does perform well with respect to these kinds of objectives when you have a ground truth. So that's sort of a nice conclusion. It's obvious that the model doesn't capture reality, but the conclusions about the Kameny rule being a good rule are still relevant in practice as well. Okay, so I want to use the last 14 minutes to just tell you about a couple of other related models, just on a high level, what the model is. So on a very high level, the two models that I want to tell you about are both under this framework of random utility models. So it's a different way of generating rankings compared to the Mellows model. And the idea is that we have a bunch of parameters, one for each alternative. And like before, M will be the number of alternatives. And then for each alternative, we have a utility distribution for that alternative. Okay? And the way the model works is we'll draw, for each voter, we'll draw his utility for alternative J from its distribution. And then the ranking will be consistent with the utilities that we drew from the different distributions. So the voters are going to rank the alternatives based on the utilities that they drew from the different distributions. So the probability of like x2 being ranked above x1, being ranked above x3, given the parameters, is the probability when each utility is drawn from the relevant distribution that the utility of 2 is greater than the utility of 1, which is greater than the utility of 3. So just to illustrate this a bit more, let's say that we have these three alternatives, red, yellow, and blue. And this is the probability distribution over the utility of red. The blue distribution is the probability for blue, and the yellow distribution is the probability of the utility for yellow. So then we draw, like if we want to generate a single vote, we draw three samples from these three distributions. So for yellow, we drew this sample from the yellow distribution. For blue, we drew this sample. For red, we drew this sample. And then we look at the samples, we're like, oh, blue, which is, let's say, x2, this is the distribution for 2, is greater than yellow, which is 3, which is greater than red, which is 1. So we got the vote x2 above x3 above x1. Okay. And if you want to draw a profile, so for example, for 3 voters, we just do this process for every voter separately. So we have for voter 1, we draw 3 samples from each distribution, and we get yellow above blue above red, which is this. For voter 2, we draw a sample from each distribution, we get this. For voter 3, let me correct this. For voter 3, we again draw 3 samples, and we get, we get a different order. And all of these are independent. So when you generate an entire preference profile, the probability of getting all of these rankings given the parameters is just the product of probabilities of getting each individual ranking given the parameters. So that's sort of the high-level framework for these random utility models. Okay. So by the way, notice that sampling a vote is pretty easy, right? Like if you can sample these distributions, you just sample from each one and you look at the utilities. So that's like that problem is really easy. But some other problems can be hard. So here's like one concrete example of a random utility model called the Thurston model. So here the idea is that each distribution is a normal distribution. Okay, so now we're instantiating what these distributions are. It's a normal distribution, and the parameters give you the mean and the standard deviation of this normal distribution. So every alternative has its own mean and standard deviation for this utility distribution. Right, so it might look something like this. And then, right, so we have this. So one sort of interesting factoid about this model is that this problem of computing what's the probability of a ranking given the parameters, that's believed to be a hard problem. It's just like a horrible integration, and like nobody knows how to do this efficiently. So that's sort of one instantiation of a random utility model. Another one is called the Plackett-Luce model. So here, instead of a normal distribution, we have something called the Gumbel distribution. I actually don't want to tell you what a Gumbel distribution is, because there's a much nicer interpretation for this model. And the interpretation is the following. So imagine that the parameters are actually weights for the different alternatives, W1 to Wm. And the probability that we draw this ranking, xj1 above xj2, blah, 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 given the weights, this probability is the weight of J1 divided by the sum of all weights times the probability of J2 divided by the sum of weights except J1. and so on. And finally, we're left with only two alternatives, and then we get like the probability of j m minus 1 in the penultimate position is his weight divided by the sum of the two remaining weights. Okay, so here's a nice way to illustrate this, which is, I think, more intuitive. So the nice way to think about it is this urn model, where we have this urn. For every alternative, we have a number of balls in the urn that is equal to its weight. So here we have three alternatives, yellow, blue, and red. And we have 4 balls for yellow, 3 balls for blue, and 2 balls for red. And now in order to rank, what we do is every time we reach into the urn, we take out some ball, and we put the alternative corresponding to that ball in the next position. Right? So let's say that initially we reach into the urn, and we get a yellow ball. So we're going to put A first. And now we either remove all of the yellow balls, or anytime we get a yellow ball in the future, we just put it back or take it out, whatever you want. And now, so we can ignore the yellow balls. So now we have 2 red balls and 3 blue balls. And again, we reach in, take a ball out. And let's say we got like a red ball, and then we only have blue left, and we put it in the last position. So what's our probability of getting this ranking, given that the weights are 4, 3, and 2? So initially, to put yellow first, we had 4 yellow balls out of 9 balls overall. So that's 4 over 9. And then we had to choose a red ball when we had 5 balls. So that's 2 over 5. So that's the probability of getting this ranking given these weights or number of balls, which is exactly this thing. Okay, so this urn interpretation is exactly this interpretation, which is equivalent to the Plackett-Luce model with the Gumbel distribution, if you happen to know what that is. Okay. Cool. So just a final remark before we finish. So this whole lecture was just meant to give you a taste of how we think about these cases of we have a ground truth. How do voters generate their votes given a ground truth? And then what do you want to do in this situation? Like which ranking do you choose? But and all of this was sort of in the context of social choice, aggregating people's opinions. But there are also a lot of interesting applications that are closely related and are not in the social choice space. So, for example, instead of pairwise comparisons done by voters, a very natural setting is when the comparisons between alternatives actually correspond to competitions between players. So you can think of the alternatives as players in some games, and then the comparisons are competition. So A plays against B, and then they can win or lose. And in this kind of setting, what we typically want is to maintain some ranking over all players. And every time there's a new competition, we want to update our ranking. Okay, so given the new information, so now we have more evidence that A beats B. Now we need to update a ranking of the different players given this new information. So this, one very famous example of this kind of system is the ELO system, which is used for a number of games. One of them is famously chess. So it's been used since the 60s, I believe. And in the first decade or so, since it was invented, it actually used the Thurston model. So the idea is that, the way you think about, we have 2 players, now they're playing a game. They both have some distribution over the quality, but every time they play a game, you sort of draw 2 samples, and then you say the probability that A will beat B is the probability that when I draw a sample from the normal distribution of A, it will be higher than the sample drawn from the normal distribution corresponding to B. So that's kind of the idea behind that system. And it's used these days for a couple of different games. At some point they switched from the Thurston model to a different model, but it's still kind of the same idea. And more recently, for those of you who have an Xbox, these kinds of games are not my cup of tea, but there's a very popular game on the Xbox called Halo. It's a first-person shooter. So people play against each other in teams in this game, and there is a ranking of all of the players in the world, based on this information. And the way this is done is based on a model very similar to the original ELO model. A complication here is that often you have players competing in teams instead of individual players competing. So you have to deduce from that how much to change the individual qualities of players. So there's definitely complications around that, but this system actually does use the Thurston model to this day. So that's like another nice application of the same kind of reasoning. That's it. So next time, actually, Shayan will be giving the lecture. The 3 next lectures will be Shayan, and then Zico and I will be back for the last lecture and do this Q&A thing.